Chapter 11 takes a look at gases and the gas laws. What we're going to do here in the first video, we'll just take a look at the general properties of gases. The second video will show you how to do some calculations, okay? So, first thing to know about gases. Gases are an interesting phase of matter. In a typical gas, here's a picture of gas particles. Most of a sample of a gas is empty space. Just a whole bunch of emptiness and an occasional molecule or atom of the gas flying around here. Truth be told, this picture is probably making it look more crowded than it really is in a typical gas specimen. Most of a gas, huge volumes of empty space in between individual molecules. You have virtually no intermolecular forces operating between them. There's always some intermolecular forces. But this gas particle is not in any way really attracted to this gas particle. Here all they're showing is two gas particles that bump into each other. They bump into each other, fly apart. The gas particles don't really stick together or get attracted to each other as they would in a liquid or a solid. So, some of the properties of gases, due to the fact that they're mostly empty space, gases are highly, highly compressible. It shows you that in your textbook here. Shows you shows you this picture of a gas inside of a cylinder here, and then here's a piston which you can push down, a little plunger or piston you can push down. So if you apply pressure to this plunger, the sample of gas gets compressed. The gas particles are forced in closer and closer to each other. Now, that's a huge contrast with liquids or solids. Liquids are not compressible. So here they're showing you that same example with a liquid here. Here's your liquid in the cylinder. Here's your plunger. Here you're applying force to the plunger. The liquid doesn't budge. Liquids are not compressible. You can press as hard as you want here. Those molecules of the liquid aren't going to get any closer to each other. Liquids are not compressible. Now some of you might say, what if you keep pressing really, really hard? Eventually, you could probably rupture the side of the cylinder, blow the cylinder out, but will just applying pressure here make the liquid smaller? Will it shrink down the volume? Nope, not at all. Liquids are not compressible. Solids are not compressible. Gases, on the other hand, are highly compressible. You apply pressure, and that gas takes up smaller and smaller spaces. The gas compresses. Another property of liquids, I remember when I first took chemistry and they told me this when I was a little confused. Liquids versus gases. Gases take the shape of the container they're in, liquids don't. And that confused me because here's a container, here's a liquid, here's some water, I pour in there. And you might think, oh, hey, that water here is taking the shape of the bottom of this container, right? So I was always confused when they said gases take the shape of their container, liquids don't. Well, here's what they mean. If it's a closed container, excuse me, let's seal it up there. There's my container. Is this liquid taking the shape of the whole container? Is it expanding to fill the whole container? No, it is not. So the liquid, yeah, it takes the shape of the bottom of the container. Does it take the shape of the entire container? No. Now, if that were a gas, if I had a container and I put a little sample of gas in there, that gas is going to expand and fill up the whole container and take the shape of the container. Gases expand uniformly and they take the shape of the container. So that's one of the properties of gases. They tend to expand and take the shape of their containers. Now, another thing we have to talk about with gases is measurement of pressure. Anytime you're handling a gas, you have to express the pressure that the gas is under. Now, the way pressure is meant, well, first let's talk about what pressure is due to. Going back to your book again. Your book has this nice little picture showing you what causes a gas to exert pressure. Oh, quite simply, individual particles of the gas slam into a surface. When that gas atom or that gas molecule hits that surface, it's applying a force to the surface. So the pressure that you experience when you're in contact with a gas is from zillions and zillions and zillions of little collisions with the surface. You see these gas particles colliding with the surface. That's applying a pressure to that surface. One atom, one molecule, virtually nothing. But if you have zillions of gas particles hitting a surface, it's going to push on that surface. A quick discussion of the importance of pressure. Let's say this is a house, and that house is filled with a gas. You have gas molecules, gas atoms, particles in the air, and those particles of the gas are bumping into the wall. They're applying a pressure to the wall there. That pressure is trying to push this wall out. Well, the wall never goes anywhere because on the outside of the house you have gas particles applying pressure in the opposite direction. So if you get the same pressure on both sides of the wall, nothing happens. If you live in a place where there's lots of tornadoes, occasionally after a tornado goes through you see damage from the wind. You also occasionally see a house where it looks like the house almost exploded. What happens is that tornado comes through and that tornado will suck some of these gas particles away. So suddenly the pressure here is less than the pressure here. So you got more pressure inside the house. What happens to that wall? That wall blows up and it just kind of flies out towards the tornado. So the house literally can explode. If you actually live around places where tornadoes hit, it's kind of weird. What they tell you to do, if there's a tornado coming, they tell you to open your windows. Why do you open your windows? Oh, that way when the tornado comes through, that extra gas pressure just goes out the window and your house doesn't blow up. So that's pressure. It's due to the collision of atoms with a surface, the gas molecules or gas atoms. Now, the way it's measured, classic way of measuring pressure is with a barometer. That's pictured here. The way this is set up, this is liquid mercury. Mercury is a liquid metal. It's very, very dense, quite heavy. You start with a long, thin tube that's completely filled with mercury. You'd start with this tube being 100% filled up with mercury. You cover one end, you flip it upside down, put it in a pool of mercury. Well, mercury is this really heavy liquid. What's it going to do? That mercury is going to flow down, so the mercury flows into this pool. But it doesn't drain all the way. Why doesn't it drain? Oh, as the mercury leaves the tube, it leaves a pretty good vacuum here. You have pressure from the atmosphere, all these atoms of nitrogen and oxygen in the atmosphere slamming into the surface of this pool of mercury. That's applying pressure to this mercury. That pressure pushes the liquid mercury. All that pressure will push that liquid mercury up the tube. And it turns out, under normal conditions, we're never normal in Albuquerque, we're a mile high, but if you were at sea level, the pressure is enough to push that liquid mercury that far up into the tube. So you have that pressure pushing the liquid mercury up the tube to a height of 760 millimeters. The only calculation I'll show you in this video, you have to be able to convert between millimeters of mercury and atmospheres of pressure. So a good day at sea level, atmospheric pressure is 1 atmosphere. 1 atmosphere of pressure is 760 millimeters of mercury. And it's kind of odd that you would measure pressure with length. Millimeters, that's a measurement of length. But it's telling you, hey, 1 atmosphere of pressure is enough to lift a column of mercury up. 1 atmosphere of pressure is enough to force a column of mercury up that high. So you have to convert between millimeters of mercury and atmospheres sometimes. It's an easy conversion. Of course, given this, you can say there is 1 atmosphere per 760 millimeters of mercury. That's your conversion factor. It allows you to change millimeters of mercury into atmospheres of pressure. So let's say you have a gas with this pressure. How many atmospheres is that? So many millimeters of mercury. 1 atmosphere for every 760 millimeters of mercury. And you would end up with, that's 2.70 atmospheres. For what it's worth, there's other units of pressure. You might see PSI, pounds per square inch. When you're filling up the tires on your car, you measure the pressure inside the tire with pounds per square inch. I think it's 1 atmosphere of pressure is, it's approximately 14 pounds per square inch. So different units of pressure. Pounds per square inch, millimeters of mercury, atmospheres. What you really have to be able to do is this type of conversion here. Make sure you can change millimeters of mercury into atmospheres. And guys, 1 atmosphere of pressure is a lot. If you have a house, 1 atmosphere of pressure inside, and you drop the pressure down to 0 here, that house is going to blow apart. Doesn't take much pressure to do a lot of damage. Okay, the gas laws you have to be familiar with, and these are covered in your book. The first one is Boyle's Law. Your book, I think, has a better picture than what I could give you here. I photocopied this right from the book, but in living color, there's your picture. Boyle's Law says that the volume of a gas is inversely related to the pressure. So you have the same gas sample here. Here the gas is at 1 atmosphere of pressure. Here that gas is at 2 atmospheres. Hey, it's pretty straightforward. As you raise up the pressure, the volume gets smaller. So, increase the pressure, the size of the gas sample is going to shrink. They call that an inverse relationship. So, Boyle's Law says that volume and pressure are inversely related. As one number goes up, say the pressure goes up, the volume goes down. Now, Charles' Law. Charles' Law relates the volume of a gas to temperature. And that one says that volume is directly related to temperature. In other words, if you raise up the temperature, you also raise up the volume. So in your book here, they're showing you a balloon, same sample of gas, just changing the pressure. Low temperature, it takes up less space. If you increase the temperature, that gas sample takes up more space. So volume is directly related to temperature. As you raise up the temperature, you also increase the volume. Last gas law to talk about then would be Avogadro's law. Avogadro's law is not at all intuitive. The last two, probably pretty intuitive. You know, you put pressure on a gas, the gas is going to shrink up. You heat a gas up, the gas is going to expand. People have a good gut level feeling for that. Avogadro's law is weird. Avogadro's law says that if you have samples of two different gases, both of them at the same temperature, the same pressure, and the same volume, they contain the same number of gas molecules, or same number of gas particles. So if I have a sample of carbon dioxide is a heavier gas. It weighs 44 grams per mole. So if I have a sample of this, and I have a sample of hydrogen, hydrogen's a very, very light gas. It's 2 grams per mole. Same size sample, have the same size sample, and they're both at the same pressure and at the same temperature. I've got the same number of CO2 molecules as I have H2 molecules. So same volume, same temperature, same pressure, I'll have the same number of gas particles, even though this guy is much, much heavier. He's a much heavier gas than this guy. And yet they take up the same amount of space. Your book kind of shows you a picture of that here as well. It shows you 1 mole of helium, which weighs 4 grams per mole. 1 mole of xenon, which weighs 131 grams per mole. So the xenon weighs a whole heck of a lot more. But let's say you happen to have the same volume of this one and this one, and they're both at the same temperature and at the same pressure. You've got the same number of gas particles. So you see here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can guarantee you over here we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Same volume, same temperature, same pressure, same number of gas particles. Even though the two gases are radically different. This one's super light. This one is super heavy, but you'll still have the same number of particles. What they're showing you here, by the way, is something called the molar volume of a gas. They define a certain set of conditions as standard temperature and pressure, STP. STP refers to a pressure of 1 atmosphere and 0 degrees Celsius. So STP, 1 atmosphere, 0 degrees. At that combination of temperature and pressure, 1 mole of any gas happens to take up 22.4 liters. That'd be about 5 gallons or so. So if you picture a 5-gallon gas can, that's about a mole of gas at 1 atmosphere and 0 degrees. So at that special combination, 1 mole takes up 22.4 liters. That's not true for liquids, it's not true for solids, it's only true for gases. So those are your gas laws. Typical gases, things you gotta know about them. Very low intermolecular forces, lots and lots of empty space. Don't worry about the elastic collisions, but do know that gases will expand to completely fill whatever container they're in, whereas liquids do not expand to fill their containers. And of course know that gases are highly compressible, liquids and solids are not. We'll move on to calculations in the next video.